Okay, thank you. Okay, I guess I can welcome you, everybody, to the third day of this workshop. And we're about to start. All right. Are you ready, David?
I'm ready.
Yeah, okay. Okay, it's my pleasure to introduce you, David Radice from Penn State. So, David, take it away.
Okay, thank you. Let me start by thanking the organizers for putting this nice workshop together. We already had a lot of interesting discussions, and I'm looking forward for more. And for giving me a chance to tell you about the work that we have been doing here at Penn State and in collaboration with collaborators in Germany and Italy as part of the core collaboration. Feel free to interrupt me at any time during the talk. I cannot see the chat or if you raise your hand, but feel free to jump in. I'd like to start with one slide of advertisement for our code called Whiskey THC, because this is an open source code that you can go and download from this web page. Not only we make available our code, but also our initial data is available, our par files are available, and also sample outputs. So essentially, it comes with everything that you need in order to verify or falsify what I'm going to tell you today. We also recently released the subgrid turbulence modeling as part of the public version of this code. So if there is time at the end, I will tell you a little bit more about what is inside that module. Whiskey THC is built on top of the Einstein Toolkit, which is an even bigger collection of open source tools for numerical relativity that I'm sure many of you know very well. This is a diagram that shows what we know today about binary neutron star mergers, starting from their in-spiral to their merger and post-merger. I'm sure that you have seen this many times, but one thing that I want to emphasize is that as we go from in-spiral to merger and post-merger, as we advance in time along this axis, we also go from periods or phases in the evolution that are relatively well understood, in which we have under control systematic errors, or at least we know how big our errors are with precision, towards phases of the evolution that are progressively less well understood because the physics becomes more complicated and the simulations become more challenging. So we'll roughly divide this talk in two parts. First, I will tell you about the work done, especially concerning the merger phase and implications that this part has on the multi-messenger signals from binary neutron star mergers. And later I will tell you about the post-merger phase and what we can learn from that and what we need still to do. But keep in mind that as we talk about the post-merger, things become more and more qualitative in nature. So let's start with in-spiral merger and early post-merger. So the first thing that has been observed for many years in the case of binary neutron star mergers is that at the time of merger, there are essentially two outcomes. Either the stars form black hole right away, and in this case, an horizon is formed at the collision interface between the two neutron stars, and the stars just fall inside. We think that these events, especially for mass ratio close to 1, are essentially electromagnetically quiet. Otherwise, if a black hole is not immediately formed, the remnant bounces back at least once and forms a massive neutron star, sometimes called hypermassive or supermassive neutron star, depending on the mass of the binary. This massive neutron star may survive for a short amount of time or for a very long time before collapsing to a black hole, or it may even become stable. But the important thing is that there's this bisection here at this point. So what can we learn from this? So one thing that has been also known for a long time is that at least for equal mass binaries, the condition for the formation of a black hole promptly depends only on the total mass of the binary. So if the total mass M1 plus M2 is larger than some threshold mass, then a black hole is formed promptly. And it has also been known for a while that this threshold mass is proportional to the maximum mass of a neutron star predicted by the equation of state. This is unknown. And some threshold constant that varies in the range between about 1.2 and 1.6. And what has also been known for a while, at least since this work by Kento Tokezaka, is that this threshold constant is related to the maximum compactness of neutron stars. So this threshold constant depends on the equation of state, but doesn't depend in an arbitrary way on the equation of state. To linear order, it only depends on one parameter of the equation of state that can be taken to be the maximum compactness. And this has really been systematically studied by Bauswan and collaborators, starting from their work in 2013, and then by many authors in the literature. So people have calibrated very precisely this threshold, the correlation between this K threshold and the maximum compactness. So recently we have also revisited this using full numerical relativity simulations, so not conformally flat gravity simulations as in the studies by Bauswan and collaborators. And in a study that has been led by a postdoc at Penn State, Rahul Kashyap, and the student Abhishek Das, we have performed close to 300 numerical relativity simulations spanning a wide range of equations of state. And we have collected all our results here, all of these red dots. So what we were originally trying to do is to break this relation. So we chose equations of state that had phase transitions, or that had common radii at, say, 1.6 solar masses, but different maximum masses and things like that. But it turns out this relation is actually quite robust. What we did find, however, is that there is a systematic shift with respect to predictions from conformally flat gravity. So although we agree qualitatively with results from Bauswan et al., we find differences in the precise numbers that one needs to take into account if we want to do multi-messenger analysis with this data. But overall, our data are actually in good agreement with previous simulations by Kento Tokezaka, although we have smaller error bars because we perform more simulations. So what can we learn from this relation? So here I'm going to follow an idea that was proposed originally by Bauswan and collaborators, and that we have kind of revisited with improved numerical relativity data and adding some additional constraint coming from a large study of phenomenological equations of state we have performed. So here the idea is that the threshold mass is proportional for this K threshold, this quantity here in parentheses, is proportional to the maximum mass of a non-rotating neutron star. K threshold is proportional to the maximum star compactness, this quantity here, and there are two coefficients A and B that we can infer from simulations. Now, the key observation that Andy Bauswan made is that if we fix R max, say we choose 12.5 kilometers for the radius of the maximum mass neutron star, then this relation is a curve in the plane M threshold M max. This curve here, for example. And now what we can do is we can plot constraints on this plane and rule out some regions, and then by that exclude some possible neutron star radii. So let's see how this works. For example, we know that the maximum mass of a neutron star has to be at least 2 solar masses, because we know neutron stars that have masses of about 2 solar masses. From our phenomenological study of parameterized equations of state, we know that the maximum mass cannot be larger than about 2.9 solar masses if we take the latest LIGO results into consideration. So this region is also excluded. A corner here is excluded by causality because stars cannot be too compact. And a similar constraint can be obtained with phenomenological equations of state. It's a little bit more stringent. And similarly, mostly because of the upper limit we have on the tidal deformability, we can exclude equations of state that are too stiff, so they produce too large neutron star radii. And so we can cut out also this part of the plane. Finally, from 17017, we know that the threshold mass cannot be smaller than 2.73 solar masses, because this binary had a bright electromagnetic counterpart, and so we can confidently say that this was not a prone collapse. So this region here is also excluded. And now what we can do is we can plot the curves corresponding to the radii that parallelly pass through the allowed region. And this gives us a constraint on the radius of the maximum mass neutron star. Now we know to be between 9.82 and about 14 kilometers. We have also extended this work to unequal mass binaries. So what we have done is we have computed here the threshold mass for different binaries as a function of mass ratio divided by the equal mass threshold mass. And we have looked at the behavior for different equations of state. What we find is that in contrast with what claimed by previous authors, there is no universal relation between the threshold mass at some given mass ratio and the mass ratio. So this ratio depends on the equation of state. And it depends on the equation of state in an interesting way, because if we are able to measure the threshold mass at some given mass ratio and at mass ratio 1 or at two sufficiently well separated mass ratios, then it turns out that we'll be able to constrain directly the compressibility of matter at maximum density achieved in the maximum mass neutron star. So this Kmax is there's a parameter in the equation of state that gives us the compressibility of matter. And here alpha L and alpha H are the slopes of these lines, and we find that they correlate very strongly with Kmax. So if we are able to measure the threshold mass at two different masses, then we can say something about the equation of state at extreme densities directly. Going beyond this and generalizing this approach, what we really want to do is do multi-messenger parameter estimation. So what we really want to do is find posterior for parameters, for example, parameters in the equation of state or parameters that are derived from the equation of state, like the tidal deformability of neutron stars, given the data that we have. And the general approach to do this is using bias theorem, so to split this posterior into a prior that we take to be as uninformative as possible, and the likelihood that depends on the data that we have observed. And so what we want to do with numerical relativity now is split this likelihood in two parts, assuming gravitational wave and electromagnetic data to have uncorrelated errors. And then we can analyze this component here with gravitational wave data analysis that is also informed by numerical relativity, because we have gravitational waveform models coming from numerical relativity. And also the electromagnetic counterpart. And here things are a little bit more complicated, because if we look, for example, at the kilonova, the light curve of the kilonova depends most directly on the properties of the ejecta from neutron star merger. So how much material was ejected, in which direction, with which composition, with which velocity. This is what determines the electromagnetic counterpart. So where numerical relativity has an important role to play is to connect these parameters here of the ejecta with parameters of the equation of state or parameters of the binary, for example, the mass ratio and the tidal deformability, so that we can put this likelihood on the same footing as the gravitational wave likelihood, and we can do a combined analysis. So this is the most general approach of using simulations to constrain the equation of state. It essentially generalizes also these phenomenological constraints that we have obtained with the Pronkor labs. This has been done by many authors, including ourselves, and I'm showing here this result collected by Breskin and et al. That includes some of our analysis using slightly different approaches shown here, as well as previous results. And the good news here is that as a community, we are kind of converging towards a common value. So we're predicting that the radius of the 1.4 solar mass neutron star, which we take to be one of the parameters in the equation of state, is around 12 kilometers plus or minus 1 kilometer. And there is good agreement between different groups. I want to emphasize that although these are all independent analysis, several of these groups actually use the same numerical relativity data, so our numerical relativity data, to derive their own constraints. So these are not really completely independent. So we have to be careful about this. One thing I want to emphasize here is that these constraints really come from understanding the dynamics of the early post-merger, because what we're really ruling out It's only the fact that there has to be some material left outside of the horizon of the black hole after merger to explain the kilonova. So we're not really using or predicting what happens to this material once it's formed and is ejected from the binary original accretion disk. In principle, if we had reliable models of the long-term evolution, we could do much better because we would be able to exclude situations in which there is enough material outside the black hole to potentially power a kilonova, but because of the way this material evolves, actually this is inconsistent with observations. So there is a lot of potential to improve these estimates, but they rely on us understanding the post-merge dynamics. So now let's get to the post-merge dynamics when things become a lot more complicated and much less well understood. Well, one thing that I will argue is quite robust, and I think we understand well, is the fact that the post-merger gravitation wave signal is characterized by features, and in particular there is one called F-peak or F2 in the literature that appears to be very robust. Different codes will agree on the same F-peak for the same binary. If you try to include effects like viscosity, magnetic fields, rotation, unless you crank up these effects to very large values, so you use extremely large magnetic fields or spin, the F-peak does not significantly change. It does move a bit around, but F-peak seems to be quite robust. And so for this reason, there have been a lot of ideas and proposals for how we can use a possible measure of F-peak to constrain the equation of state of matter at extreme densities and temperatures, such as those achieved in the post-merger. And there are many, many ideas in the literature. Here I want to highlight one that we have recently put out, in which we have noticed that there is a characteristic radius of the remnant that can be constructed using this frequency that we call the Keplerian radius here. And that this radius has a universal relation that links it to the maximum density achieved in the maximum mass neutron star. So basically what I'm saying is that the different binaries will have different peak frequencies depending on their equation of state and their masses, but all of them will lie on this curve after we normalize the peak frequencies with the mass of the binary and we rescale things in this way, then we find a universal relation. And this includes also equations as they have phase transitions, hyperons, and quite a different nuclear physics. So what we can do with this observation is if we measure F2, then we can put a constraint on the maximum mass, on the maximum density in the maximum mass neutron star, and this can lead to a very strong constraint on the equation of state, even for a detection at a very low signal-to-noise ratio. So for example, in this case here, this was for a detection with signal-to-noise ratio 7 in the post-merger, which is the minimum that you require in order to claim a detection. There are other things that happen in the post-merger that we hope to understand and that may or may not be revealed by just looking at the peak frequency. For example, one possibility that has been discussed in the literature often is the possibility of quark depth confinement in the post-merger because of the high densities and temperature reached in the remnant. Now, according to some equations of state models, it's possible that this deconfinement will show up in a deviation from of the F-peak from what is expected from universal relations. However, in other models of phase transition, for example, the ones that we have considered with our collaborators in a study led by Viral Prakash, a student here at Penn State, we find that actually the deviation on F-peak can be very small and essentially not detectable for a generic binary neutron star merger, at least for this equation of state. Instead, we find that the phase transition, in this case, is encoded in the lifetime of the remnant in things like the binding energy of the remnant and possibly in signature of the electromagnetic counterpart from these mergers. So there are other things in the post-merger essentially that we hope to learn and that cannot be directly extracted from the peak frequency. So other things that we hope to understand, for example, here the phase transition could be revealed if we have a way to measure the lifetime of the remnant. And in this case, there are some ways that have been proposed to measure this lifetime. One is if we have a very strong gravitational wave signal in the post-merger, we can obviously see the point at which the signal shuts off. If it shuts off abruptly, we can confidently say that this was a prompt collapse. Meanwhile, we wait for third generation detectors that will be needed in order to make this type of observations. We can hope to say something about the fate of binary neutron star mergers by looking at their electromagnetic counterpart. And here an idea that has been around for a number of years, first proposed by Brian Metzger, is to look at the composition of the ejecta. Because it turns out that if the massive neutron star produced in the merger survives for a very long time, this will irradiate the ejecta, change their composition as predicted in these simulations from Lipuner and collaborators. The composition here in terms of proton fraction of the ejecta will be reflected in the final nucleosynthesis abundances that we can then constrain either by looking at the color of the kilonova or maybe perhaps in the future also with spectroscopy. So in principle, this is a really great idea and an opportunity for us to learn about the post-merger. Of course, the problem here is that these simulations were rather simplified and idealized, so they are fine if we want to compute the qualitative behavior of the system, but if we want to quantify precisely how the composition of the ejecta depends on the lifetime of the remnant, we'll have to perform numerical relativity simulations with real neutrino transport, while these were Newtonian simulations with a local prescription for the heating rate. So this is something that as a community, I think we are attempting to do, and there are multiple groups working on this front. On our side, we have focused on performing long-term simulations with neutrinos in full 3D. And since we try to do things in full 3D with a hypermassive neutron star also, or a massive neutron star left at the center, we have not yet been able to really push this to many hundreds of milliseconds in the post-merger, but we can start to study properties of the neutrino-driven wind and of other viscous and hydrodynamically launched winds that are present in the post-merger. One interesting thing that we found is that if the massive neutron star survives and does not collapse to black hole, then there is a robust mechanism to drive outflow with moderately large velocities that we have called the spiral wave driven wind. So here the mechanism is that the massive neutron star deforms due to the so-called low T over W instability and develops an M=1 feature in the density. This feature then launches waves in the accretion disk, and these waves turn out to transport angular momentum outward. So what you can see here is a volume rendering of the flux of angular momentum carried by these waves, and you can see that a color red means that these are carrying out angular momentum and unbinding material. You can see here the mass ejection rate as a function of time in milliseconds from the merger. And we can see that once this wind starts to develop, it proceeds and has almost a constant mass ejection rate and continues until a black hole forms. For example, in the case of this LS220 binary, black hole formation occurs roughly around here, about 25-30 milliseconds after merger. At that point, the spiral wave wind dies off. So this is interesting because it provides a natural explanation for the blue kilonova. The spiral wave wind is something that we see naturally in the simulations. We don't have to put anything or assume anything. It appears in all of our simulations as long as the remnant is long-lived. So if we are we need to accept a long-lived remnant, and this provides a natural explanation for the blue kilonova. And here by long-lived, I mean that if we extrapolate our simulations from 100 milliseconds until the time when we have enough mass ejected to explain the blue kilonova, we have to wait for another 100 milliseconds or so. So we need to invoke a remnant that survives for about 200 to 300 milliseconds. What our models actually cannot explain self-consistently is the red kilonova. So for that, we need to invoke some mechanism that will take place after black hole formation that produces sufficiently neutron-rich outflows. And here a proposal that has been made by Daniel Siegel and others is that the winds from the disk may produce these outflows. But again, we don't have self-consistent simulations that produce that. So what I'm showing here in this diagram is a light curve in which the red model is this long-lived remnant that we have evolved for 100 milliseconds after merger. And here, in order to explain the infrared data, we have to artificially increase the amount of ejecta mass by a factor of a few. Neutrinos play an important role in the post-merger, as we were discussing, because they irradiate the outflow and they change their composition. So we have also started to investigate carefully the neutrino emission from neutron star merger remnants. And we have collected the results from a large sample of simulations in this paper here that was just published. We find a few things that were not perhaps a surprise, but what we find interesting is that there are some things that are very robust as a function of equation of state and properties of the binary, such as the masses of the two stars. For example, we find that the average energies of neutrinos at infinity are roughly independent on the equation of state. There is always a clear hierarchy, with the heavy lepton neutrinos being most energetic, the anti-electron neutrinos being intermediate, and the electron-type neutrino energies being the lowest. We understand this because the heavy lepton neutrinos decouple at higher densities and temperatures. And also we find that anti-electron neutrinos dominate because after the merger, because of the increased density in the remnant, is actually more energetically favorable to protonize the remnant. So instead of deleptonizing like a core collapse supernova remnant, a proton neutron star, the neutron star merger remnant tends to releptonize. And so these electron type neutrinos are instead released mostly from the accretion disk, so they have lower energies. We have looked also at the distribution of the neutrinos around the remnant. And again, one thing that we find to be quite interesting is that neutrinos are geometrically focused in the polar region. This is also the region where our numerical scheme has the largest error. So this is perhaps a problem for us in the future. And we find that instead material ejected close to the orbital plane is shielded from strong neutrino radiation by the disk. So it's not subject to the strong neutrino radiation from the remnant neutron star, but is shielded. And so this may have consequences for this argument on the composition of the ejectors function of the lifetime of the remnant. This is also compounded by the fact that, as Francois was discussing yesterday, the neutrino-matter interactions strongly depend on energy. And the energy of neutrinos in the polar region are higher by maybe factor 2 compared to energies in the equatorial region, where we have lower energy neutrinos coming from the accretion disk primarily. And this compounds that effect and makes it so that the composition of the outflow is strongly dependent on the angle. So material tends to be significantly less neutron-rich and can be even proton-rich if it is ejected along the polar direction, and is instead more neutron-rich if it is ejected along the orbital direction, orbital plane. We have also looked at how the composition of the outflow depends on the numerical approximation done for neutrino radiation transport. And we find that there are some systematic differences between all of these different approaches, as anticipated. However, overall, the effect on the final composition is only about a factor of a few. One last thing that I want to comment on is the importance of the hydrodynamic effects on the evolution of this ejecta once it is launched from a neutron star remnant. So we have taken output from our simulations, including this long simulation that we run for 100 milliseconds, and we have imported it into a one-dimensional Lagrangian radiation hydrodynamics code to compute light curves. Because this is a spherical code, it's probably not adequate to really make a detailed comparison between our predictions and observations, but we can use it as a way to understand systematics. For example, we have compared our hydrodynamic evolution. Here, these are solid lines, light curve in different bands, with predictions that we obtain if we assume that the material is homologously expanding. And we find that the assumption of homologous expansion can actually shift the peak of the light curve by even a few days. And so this is an assumption that is commonly made when estimating light curves, so neglecting essentially pressure forces. Similarly, and somewhat surprisingly, we find that if we change the heating rate in the ejecta by factor 3 in the first 10 seconds, and so this is spanning the current range of uncertainties in the nuclear physics. This can have an impact on the luminosity even days after merger. And this is because if you change the heating rate at early times in the ejecta, this changes pressure forces in the outflow and changes the distribution, the radial stratification of the outflow. And this is why this early time heating rate somewhat surprisingly actually has a big impact on the light curve at several days after merger. So you can see this can be even a couple of magnitudes in the worst cases. There are many things that we can do at the moment with numerical relativity. There have been a lot of success in this field in modeling neutron star merger remnants, but of course there are a lot of challenges that we need to overcome before we can completely complete our program of performing multi-messenger analysis and using all of the data that we have from optical, infrared, radio and gravitational waves, using all that we know about the post-merger evolution of bineutron star mergers. And here I've listed a few of the challenges that we face. It's widely recognized that we need to perform simulations that span at least a few seconds with full physics. And this is challenging not only because of the long time scales involved, but also because most of the neutrino approximations we make are not valid over those long time scales if there is a massive neutron star at the center. We have to be able to capture the diffusion of neutrinos from the inner core of the star out. Our simulations clearly lack the resolution to resolve all the MHD effects. So in our case, we have essentially given up on MHD so far. We have just used the subgrid models because we cannot resolve all the MHD turbulence anyway. But in the future, we'll have to also include MHD effects. And there are some effects that cannot be mimicked by subgrid models. For example, the presence of jets and these large-scale effects due to magnetic stresses that cannot be captured by a local model. There are issues that need to be solved in understanding the interaction of neutrinos with dense matter, because as we were discussing a couple of days ago, neutrinos in neutron star merger decouple from very high densities, higher than they do in core collapse supernovae, and we have already discussed the issue of neutrino flavor conversion. I think I will, in the interest of time, I will jump directly to my conclusion slide and conclude. the main take-home message that I hope you got from this talk is that numerical relativity has a very important role to play in multi-messenger astronomy because it provides a dictionary that connects electromagnetic data and gravitational wave data and brings both data sets together in terms of the same input physics, so the same equation of state and binary parameters that we want to constrain. There is a lot of work that needs to be done that I have split in kind of two main areas. On the one hand, if we want to improve current constraints, we need to explore the binary parameter space and equation of state space more systematically. When we do multi-messenger parameter estimation, we are possibly subject to systematic uncertainties. I think we understand the physics of the early post-merger, and we can debate this. But it's clearly true that we need to span a large range of binary and equation of state in order to have systematic uncertainties under control. If we want to deal with longer time scales and really make the best use of the data that we have and understand the post-merger, then there is a lot of work to be done to understand microphysics and macrophysics like turbulence and their impact on the remnant. I didn't have time to talk about the GR LES model as we have implemented in our code, so I will just leave it here for the conclusions.
Okay, thank you very, very much, David, for this great talk. We are a bit ahead of time, so I don't know if you have more slides about GRL.
Oh, okay, I plan actually for just 30 minutes, but if I have another 5 minutes, I can go back and tell you about the GRLES model.
Yes, you do.
Okay, because this is something that we have just released in the public version of the code. So the issue is how do we describe turbulence in neutron star mergers? So one option is to try to resolve all possible scales in the problem. However, if you do a back of the envelope estimate and you compute how small can be the small scales in a binary neutron star merger system when turbulence develops, you will quickly realize that this is impossible because you will have to have resolutions of the order of few centimeters. So this is not going to happen anytime soon. The idea instead with large eddy simulation is to replace the equations of relativistic hydrodynamics or magnetohydrodynamics with a new set of equations that only describes the motion of large-scale vortices, the motion of the bulk of the flow. Everything that happens at small scale is replaced in these equations, in this effective theory, by a closure, by a turbulence model. So here I have a sketch of how this works in the case of special relativistic hydrodynamics. The special relativistic hydrodynamics can be written using the momentum variables in a very simple form that resembles the Newtonian equations. And so the idea with the LES framework is that instead of solving for the momentum of the fluid at every single point, we're going to coarse grain the momentum to apply a filtering operation and only look at the large scale evolution of the momentum. So instead of evolving the momentum, we evolve a coarse grain momentum. So I do this by putting a bar on top. And to solve for this quantity, we will solve an effective equation that has this form. So if these equations were linear, then the only thing that we are doing is we are averaging the equations over some small volume, and then we will solve the equations for the average quantities, and that would be the end of the story. Fortunately for us, the equations of relativistic hydrodynamics are non-linear, which means they're interesting. And so what happens is when you apply a coarse graining operation, so a linear filter, you end up with terms that you cannot write in terms of only coarse grain quantities. For example, there is this correlation between the momentum and the velocity. And if we only know the momentum, we cannot write, or the average velocity, we cannot write this explicitly. So instead, what you can do is write this as a product of the two coarse grain quantities plus a term that we're going to model. This is the subgrid stress energy tensor. the generativistic version of the same equation is actually very similar. It's just a little bit more involved. There are more terms, but the idea is the same. We start from the Valencia formulation, for example, of generativistic hydrodynamics, and we just apply some coarse graining operator that we imagine to be a linear operation. And when we do so, we obtain equations for the coarse grain quantities. So for the evolution of the bulk properties of the flow, this is what we really care for. And again, when we do this process, we end up with terms like the averages of the spatial stress tensor that we cannot explicitly write in terms of quantities we are now evolving, in terms of the coarse grain quantities. And so we'll have to provide a closure. Some of the terms that appear in this process are listed here. There are more, especially if you include magnetic fields. The most simple to understand is this turbulent stress tensor that arises because of the correlation between the momentum and the velocity. There is a term that arises that I call here the turbulent momentum because the Lorentz factor is a nonlinear function of the velocity. So again, the average Lorentz factor is not the same thing as the Lorentz factor computed with the average velocity. And there are also corrections that appear at the level of the equation of state, because the average pressure is not the same thing as the pressure evaluated for the average density and average energy density. So there are all these correction terms. So how do we treat these terms? Well, the first thing we could try to do is simply to set them to 0. And this is called the implicit LES approach. So what we are doing here is we're solving the equations with a finite volume schema, which we are already evolving for coarse grain quantities, and we rely on the numerical properties of the scheme to provide the closure for these terms. So we don't explicitly set them. They appear just because of the truncation error of the scheme. This approach actually works, seems crazy, but it works well in applications. The problem is that in order for this to work, you need to resolve the float at very high resolution. So this implicit LES framework works only if you can resolve a large percentage of the turbulent energy cascade. Otherwise, this approach will not converge. One approach that we have experimented with is to only model the turbulence stress tensor, which in the Newtonian case is the only term that appears in Newtonian incompressible turbulence, and treat the other ones as being subdominant. And this is what is implemented in my code. So I have implemented this subgrid turbulence stress as an effective viscosity in this form here. And now we have this parameter, this turbulent viscosity. It's a free parameter that we write in terms of characteristic scale that we call mixing length and the sound speed. In our code, what we do is we fit the mixing length using results from simulations by TCAN collaborators. So what they have done is they have computed the alpha viscosity and given results as a function of density. And there is a way to connect this mixing length to the alpha viscosity through the sound speed of material and the angular velocity. So I can take these quantities here from my simulations, the alpha viscosity from the simulations of QC et al. And I have tabulated them here. These are the green dots. And what is implemented in Whiskey THC is a fit to this formula. So we have a mixing length as a function of density. It's worth spending a minute to comment on the features of this mixing length. So we find that the maximum viscosity is at the surface of the, close to the surface of the neutron star. 10 to the 11 grams per cubic centimeter is the point at which the angular velocity profile of the remnant becomes roughly Keplerian. So this is what often we call the surface of the massive neutron star. So that shear layer is where the flow is most unstable to the magnetorotational instability that was simulated by TCAN collaborators. So this is where the viscosity is largest. The inner core of the neutron star is actually stable against MRI. And so the turbulent viscosity becomes smaller there. and the viscosity outside drops simply because the angular velocity and the sound speed are smaller there. So the mixing length becomes smaller there. We have used this model not really as a way to make necessarily more accurate simulations, because this is all very qualitative at this stage, but mostly as a way for us to gauge errors and robustness of our results. For example, we have looked at the instantaneous frequency of gravitational waves after merger, and we find that it is quite robust. Unless you choose very large values of viscosity, it's difficult to have significant deviations of this peak frequency, so this quantity here. So this seems to be robust. Other things like the amplitude of the gravitational wave signal, the lifetime of the remnant are things that are quite sensitive to turbulence. So if we want to have quantitative models for those, we will have to resolve the issue of turbulence. And I think I will skip the impact on the ejecta. Okay, then I'm at the conclusion the second time. So I can say that I will argue that LES models are essential in the future to model turbulence in the post-merger evolution of neutron-star mergers. And this is just the first step. There are better models that have been now published in the literature that are also free from some of these free parameters that are included in my own model. And hopefully this can give fully quantitative predictions for the post-merger evolution of double neutron star systems. Okay, thank you.
All right, thank you again, David, for this great talk. We're right on time, so let's start with the questions. Feel free to jump in or raise your hands. Okay, I see first Udi.
Hello, thanks for the talk. I have a question about the ejector that is thrown away with spiral waves.
Yes.
What is the difference in this simulation from other simulations? So why did you see it in this one and people didn't see it in others?
So we see it in all our simulations. Many of the simulations performed by other groups are too short to see the spiral wave window. I'm not sure that others also have looked carefully in their data to see whether or not this wave is present. However, what I can say is that the presence of this low T over W, so this instability in the remnant that creates this M=1 deformation of the massive neutron star is present also in simulations by other groups. And,
this deformation produces a strong gravitational wave signal?
It produces a gravitational wave signal. It's not very strong. We have also, and other people have looked at the detectability of this signal. It's not particularly strong because L=2, M=1 is not, M=1 is not the best channel to emit gravitational waves.
So it cannot be detectable?
It may be detectable for a nearby source. So it's a little bit subtle because the damping rate of the L=2, M=1 mode is much smaller than the L=2, So over time, what happens is the L=2, essentially drops to 0 within 10 to 20 milliseconds, depending on the equation of state and other things. But L=2, M=1 persists for very long. So if it persists for hundreds of milliseconds, then it will be detectable with Cosmic Explorer. It's also a lower frequency, so that also helps with the detection. If the mode decays, then it will be difficult to detect.
So what will be your prediction for the mass ejection from a remnant which is not collapsing? So
our prediction is that according to our simulation, it's roughly the mass ejection rate is about 1% of the solar mass every 100 milliseconds.
Well, after 10 seconds, you injected the entire system.
Yeah, 100 milliseconds is 0.01 solar mass, and 200 milliseconds you get to 0.002 solar masses of ejected.
But if your initial mass of the binary is small enough, then it never collapses. So in principle, you can continue and inject more and more and more.
Yes, so eventually it will stop ejecting material. This will stop. The stop will occur either when the massive neutron star collapses to black hole, or when all the disk has accreted, because part of the material is still accreting, and over a time scale of about a second or so, the disk will either completely evaporate whatever is left of the disk, or accrete onto the central object. So at that point, the spiral wave will terminate.
So, okay. So the prediction is that lower masses,
total
masses for the binary will give you, this is just n.
Okay.
So lower total mass for the binary will give you stronger signal.
Yes. So yeah, that is our prediction. The spiral wave will also terminate once the remnant achieves solid body rotation, because at that point the low T over W instability is gone. But we have not simulated for long enough to say when that happens. So everything that I've said is extrapolating in the future from 100 milliseconds that we have simulated. So if we assume nothing changes, then it will continue ejecting at the same rate. It may be that something will change, either because it collapses or because it achieves solid body rotation or the disk is accreted. Whatever is first will terminate the wind.
Thanks. And apologies for taking so much time.
No, it's okay. Yeah, we can come back, but I want to give the opportunity to everybody. So, Kenta.
Oh yeah. Hi, David. I will be quick. So you said in challenge, you said the non-LTE radiation hydro. Does that mean non-LTE neutron transport?
Yeah, so that means that we have to worry about the fact that matter may be outside of weak equilibrium with neutrinos. And so there may be weak processes going on inside of the remnant on time scales that are comparable to the dynamical time scale. And this may show up as an effective bulk viscosity, for example, and affect the evolution of the remnant. For example, we are thinking about effects like the creation of pions and their subsequent weak reactions that may happen dynamically, so out of weak equilibrium in the matter.
I see. Interesting. Thanks.
Okay, thank you, Kenta. Vasilios?
Yes, hi, David. Very nice talk. Going back to the spiral waves, were those done with the viscosity?
We have done with both viscosity and with no viscosity, and we see them in both cases.
So you're basically saying that the continuous m equals 1 mode in the hypermassive neutron star is kind of driving the spiral waves in the disk? Because I think in the accretion disk community, the law is that the MRI, for instance, kills the Papaloisy-Pringle instability in disks, and you don't get those m equal 1 modes there.
Yes, when the massive neutron star collapses, there is no driving of this instability, and it disappears in the simulations.
Okay. And then one more quick question about the GLES, the implicit one. Do you think that using higher order methods and better Riemann solvers and everything would help with that by increasing the effective resolution?
Oh, this is a good question. I think it's very subtle, because for highly implicit LES to work, what you need is your truncation error of the numerical scheme should mimic a turbulent closure. And it's not necessarily the case that the high order scheme will do a better job than a low order scheme at mimicking what turbulence does at small scales. And here the issue is that when we think about low and high order, we are thinking about Taylor expanding the solution and matching, for example, the expansion coefficients to some fixed order. And then we say that the scheme is more accurate if it matches more coefficients. But when you have a turbulent flow that changes on very small scales, this tailored expansion on the scale of the grid is not really meaningful. And so it's not necessarily the case that high order is better.
Thanks.
It typically is, but there is no, it's not a given fact that high order means that you can resolve turbulence better than low order scheme.
Okay, thank you, Vasilios. Wolfgang's next.
Yeah, hi David, thanks for the nice talk.
Okay.
So I have two comments, one on the start of your talk and one near the end. So the first one was, you mentioned LIGO constraints on the maximum mass, but I'm not sure which you meant, because in fact there were several, and many of them used assumption if black hole is necessary for the gamma ray burst. For example, the GRB paper had the constraints assuming the mass is above the maximum TOV mass. The model selection paper had constraints assuming at collapse it was a hypermassive star, and so on. So just to comment, there's more than kilonova as also the gamma ray burst for multi-messenger. My second comment is on the turbulence thing. So this reminds me very much on the something Carlos Palenzuela did with the magnetic MHD equation. And I never quite understood why this averaging procedure and the correction terms one gets is automatically associated with turbulence. I mean, I could apply this to a perfectly smooth, analytically given fluid flow and still get correction terms. And also turbulence is something that can develop, so a flow can become turbulent, but there's no additional degree of freedom. You have closure relations that always, for a given state of the average quantities, gives you exactly one correction term. So can you comment a bit why this is not simply some more way to make it more accurate, but actually something that should describe turbulence?
Okay, thank you for these two comments. So concerning the maximum mass, I want to be a bit precise what we did there. So what we have done is we have generated a random set of 2 million equations of state subject only to causality constraint. And then we have imposed tidal deformability of the 1.4 solar mass neutron star to be less than 800. And we have looked at what is left in terms of equations of state. And there are no equations of state that go above 2.9 solar masses. So this is what we have used as upper bound on the neutron star mass. Actually, for this constraint on the maximum minimum radius, that upper bound doesn't really come into play. But this is what I have plotted in that diagram. In terms of turbulent closure, you are perfectly right that you can apply the same procedure for a smooth flow. And a good turbulent closure should then predict that this tau ij term, for example, this one should be 0. So a good turbulent closure will have mixing length going to 0 in the laminar regions. So what I'm doing now is I'm using L mix as a function of density, and I'm relying on the fact that in the regions where in the simulations of Cucci et al. The flow was laminar, the alpha viscosity was 0, and so my turbulent closure also gives me 0 viscosity there. But of course, this is a very, very crude assumption. So to do things correctly, one is to have either a model in which the mixing length is evolved or computed as part of the model. And in some of the things that Carlos Palenzuela is doing, this is actually the case. So there are formalisms in which this mixing length is not taken as additional free parameter, but comes out of the equations. And in those formalisms, the mixing length goes to 0 for a fully resolved flow. So that would be the best approach. Or what we're doing now is we're really using this as a way to gauge our uncertainty. So we're not going to claim that a simulation done with this mixing length is more accurate than one without any mixing. what we are going to say is only that this encompasses the range of uncertainty that we estimate at the moment.
Okay.
So we use
Thanks.
this
That sounds
only
perfectly reasonable.
robustness, not to. I will not claim that taking a mix with this form gives you more accurate results than setting it to 0.
All right. We're on time. We have one more question from Maria. Can you keep it short?
Yes,
Maria and David.
absolutely. Yeah, great talk. And I want to ask a very quick question about the systematic errors. Can you tell us a little bit about what are those exactly and how you take care of those?
So there are systematic errors in essentially everything that we do here. Do you have something specific in mind in which you want me to comment?
Okay, the first few slides, you started with saying that your code does report some systematic errors. And my first question was for you to identify what are those errors.
Yeah, perhaps then I can use this slide. So, so in this procedure where we have tried to constrain the equation of state using kilonova data, what we are doing is we are mapping eject and disk that we find in simulations to the tidal deformability and also the mass ratio, and then using this as input when we compute the likelihood. So basically, given lambda twiddle, we compute ejecta properties, and then this gives us the light curve and then the likelihood. And here, actually, the dominant source of uncertainty is the fact that this fits, even if we take simulations to be exact, which they are not. But these fits actually are the dominant source of uncertainty. There are features in the simulation that are not resolved by simple formulas that relate ejecta mass to Q and lambda twiddle, because there is more physics than just these two parameters. So what we do is, after we construct these fits, we estimate their errors, and then we propagate these errors as nuances parameters in the estimation of the likelihood. So every time we compute, for example, the dynamic ejecta masses, we don't just take the value from lambda twiddle and Q, but we also randomly extract a calibration error parameter in a range given by the uncertainty of the fit. And then at the end, we marginalize over this calibration parameter. So this gives us the full width of these error bars. And for more detail, you can check this paper.
Excellent, thank you.
Thank you, Maria. And yeah, thanks again, David, for this great